All right, today we're talking about a great escape. And no, not from some high security prison, but from a scientific practice that's been the standard for over a century. And the escape artists, well, they're not people. They're some of the most mind-blowing technologies you can even imagine.
You know, at the very heart of this great escape is a really powerful ethical idea, and this statement from PETA pretty much sums it up perfectly. For decades, this single thought has fueled a huge, passionate debate, both inside the scientific community and way outside of it.
And look, this isn't just a philosophical idea anymore. It is having very real consequences. Take a look at this number. Just 1,200. What could that possibly be?
Well, that's the number of pregnant rats and their babies who were spared from a single chemical test that got called off in 2025. I mean, think about that. This isn't just some abstract statistic. It's a really powerful sign of the massive shift that's happening right now.
In this one victory, as big as it is really just one piece of a much bigger story. We might be looking at the beginning of the end for an entire era of research, and the answer to a dilemma that has haunted scientists for years.
See, the problem has always been two-sided. First, you've got the ethical dilemma, right? The moral questions are pretty clear. But then there's the other side, a huge scientific roadblock. The genetic and physiological gap between animal models like mice or rats and us humans, it can be absolutely massive. A rat's brain just isn't a human brain, and that simple fact can lead to results that aren't just unreliable, they can be dangerously wrong.
So what changed? Why is all of this happening now? Well, it's not just about activists anymore. What we're seeing is a global tidal wave of policy changes coming from the very top. Governments, regulatory bodies, they're all finally moving in the same direction.
I mean, just look at 2025 alone. It was an absolute whirlwind. Early in the year, the U.S. National Institutes of Health made a huge commitment. Then, boom, Health Canada followed. By the end of the year, the UK had a full roadmap, and the US FDA announced major changes for antibody therapies. It was like a global domino effect, with one country after another jumping on board.
And this isn't just empty talk. This quote, directly from the FDA, it's a total game changer. They're not just allowing these new methods, they're actively building them into how they make decisions. This is a fundamental change to the very DNA of how drugs get approved.
So, what's actually making this huge global shift possible? It's not just good intentions, right? It's the technology, and it is incredible. So let's look at the first major tool that's making all of this a reality.
It all boils down to solving this one almost science fiction-like problem. How on earth can you test the effect of a new drug on a human brain without actually having a human?
The answer, honestly, looks like something straight out of a movie. They're called organoids. You can think of them as mini-brains, or maybe like crash test dummies for human cells. These are tiny, self-organizing 3D cultures grown from stem cells right in a lab dish, and they can actually replicate a ton of the complexity of a real human organ.
Now here's why that's so important. These organoids allow for what's called high-throughput screening. Basically, scientists can test thousands of different compounds all at once, getting super accurate data on how those drugs affect specific human brain cells. That's a level of precision that was just impossible before.
But there was a catch. Even these amazing organoids had a hidden dependency, a secret tie back to the old way of doing things that had to be broken. And that required a second, even more advanced tool.
So here's the problem. For the longest time, the very methods that were supposed to get us away from using animals still needed animal products to work. Specifically, they relied on biological coatings that came from mouse tumors. It was a huge contradiction, ethically speaking, and it also created inconsistencies in the research that made results less reliable.
So, enter the bioporous scaffold. This is a massive breakthrough. It's a completely synthetic material, but the magic is in its architecture. It has this textured, interconnected structure that's basically a 5-star hotel for cells. It gives them the perfect environment to grow and thrive, all without any animal products whatsoever. So how do they build this thing? It's a pretty cool process, actually. They use things like microfluidics and bioprinting to shape a liquid polymer into this incredibly precise, porous network. And when it solidifies, you get this stable, bioactive scaffold, basically the perfect home for human cells. It's like building a biologically smart apartment building for them. And the results are just wow. Human neural stem cells stick to this material in under 30 seconds. That's without any animal coatings at all.
The structure itself is what makes it work. It's bioactive on its own. That is a true game changer.
So what happens when you put these two revolutionary tools together? When you combine human-derived organoids with these completely synthetic scaffolds, well, you unlock an entirely new frontier for science.
The benefits here are just enormous. You're talking about more accurate drug testing, better models for devastating diseases like Alzheimer's and stroke, the potential to speed up personalized medicine, and of course, it solves the ethical problem and lines up perfectly with all these new global rules. It's not just a win-win, it's a win for science, a win for ethics, and a win for all of our health.
Which leaves us with one last really big question to chew on. If we can now build better, more accurate synthetic models of ourselves in a dish, what does that really mean for the future of medicine? What does it mean for our ability to finally cure the incurable?